Now that we know things about sampling distributions and the central limit theorem, we can do some new problems with normal curves that we weren't able to do before. Here's an example of something that we've already been able to do in the past. A local barista started weighing the cups of coffee she filled for customers. She found that her medium coffee weighed an average of 420 milligrams with a standard deviation of 19 milligrams. And it says that her coffee cup filling followed the normal distribution. So we can assume that we started with a normal distribution. What is the probability of getting a medium coffee that weighs less than 400 milligrams? So the value that we're interested in here is 400 and downwards, 400 and less. And whenever we're doing problems with normal curves, the very first thing we want to do is turn that value of interest into a z-score. Our z-score equation says that we're going to take our value of interest, we're going to subtract our average, our mean, which we sometimes call mu, and in this case, because it's from data, is going to be x bar, and divide that by our standard deviation. And again, because this is collected from data, we're just going to use Sx instead of sigma. So now let's plug in the values. We know that our value of interest here is 400. We know that our mean up here is 420, so we're going to subtract 420. And we're going to divide by 19, our standard deviation. So in our numerator, we have 400 minus 420, which is going to be a negative 20. And we're going to take that negative 20 and divide it by 19, our standard deviation. And this is going to give us our z-score of negative 1.05 approximately. Negative 1.05. And what we did again is we took that 400 milligrams and we turned that into a z-score. Now we want to actually answer the question. What is the probability of getting a medium coffee that weighs less than this amount? Or if we were to draw our normal curve real quick, what is the probability of getting a value on this normal curve that is less than negative 1.05 on the standard normal curve? So 1.05 is going to be somewhere around here. And if I quickly shade that in there, we want to know what is the probability of being down there. Now using our calculator, we can use the normal CDF function, and we pop in two values into that function. The first one is going to be the lower end, and then the second one is going to be the upper end z-score that we're interested in. So on our lower end over here, we have, it goes on to negative infinity. So we just pick some very negative number, such as negative 1,000. That will work just fine. On the upper end, it looks like on the right side, we stop here at negative 1.05. That's the z-score that we stop at. So negative 1.05 would be our right side that we put into our normal CDF. And now we go ahead and put this in our calculator, second vars, normal CDF, negative 1,000, comma, negative 1.05. And we're going to get 0.14, and let's round it up to 3 digits, 0.147 as our probability here. So when the question asks, what is the probability of getting a medium coffee that weighs less than 400 milligrams? The answer would be 0.147. Or you could rephrase that as a percent and say there's about a 14.7% chance of getting a coffee that weighs less than this amount. We're going to try to do the same problem now with a very small change using what we know from the central limit theorem. It says here that we have the same basic information as before. We have an average of 420. We have a standard deviation of 19 and a value of interest that is 400 milligrams. And we're looking at the average weight being under that again. Here's the very slight change in the problem description. What is the probability of getting a random sample of 6 coffees, not just one, but 6 coffees that have an average weight under 400 milligrams? So instead of just having one where, any given coffee could be a little bit high or a little bit low, we're going to take 6 of them and average them together. And so you would think that is probably less likely to happen, because more than likely, if you have 6 of them and you're averaging them together, it's a lot harder to be really far on either extreme. So we're going to go ahead and find the probability and test that idea. This 6 here is the sample size, so we're going to label that n. The 420 up here was our average, so we'll label that x bar. Our 19 was our initial standard deviation of all the data, so sx. And the 400 is our value of interest, so we just call that x in our formula. So just like before, we would want to find a z-score before we proceed with our normal curve. But before we can find our z-score, we need to update our standard deviation, because we're no longer going to use sx. We're going to use sx bar, which is based on the central limit theorem. So we're going to take our old standard deviation and divide it by the square root of n, which in this case it says our old standard deviation was 19. But because we have samples of size 6, we're going to divide that 19 by the square root of 6. And what that's going to give us is 19 divided by square root 6, 7.76, let's call it. That's our new standard deviation. So from here on out, we're going to do exactly what we did on the last problem. We're going to find a z-score, we're going to find the area under the normal curve, do our normal CDF. However, this time when we do it, we have a new standard deviation. So if z is equal to our value of interest, 400, minus our mean, 420, divided by our new standard deviation over here, our new standard deviation, 7.76. Let's go ahead and see what we get. Well, 400 minus 420 is negative 20. And we're going to divide that by the thing that we just calculated, that's 7.76 there. And it's going to come out with negative 2.5. We'll go to 3 digits, I guess. Negative 2.578. That's our z-score. You'll notice that our z-score before was only negative 1 point something. Now we're negative 2.5 something. The z-score went up by quite a bit because as the standard deviation goes down, anything that's far away from the mean all of a sudden becomes amplified. It gets really far away now. So when we sketch our normal curve, 2 standard deviations, that's way out there. In 3 or 2.5, you're looking way down in the very bottom over here. So when we say negative 2.578 and below, because it says under that amount, we're coloring way down in the very lower parts of that normal curve. So again, we do our normal CDF, and we're starting on the very far left towards negative infinity, so we'll go with negative 1,000. And then on the right side, we stop at the value we just calculated, negative 2.578. So if we go back to our calculator, we do our second bars, go down to normal CDF, and type in negative 1,000, comma, we'll just do our last answer so we don't have rounding error. And we get 0.00496. And if we round that off just to the simple 3 decimal places, 0.005, or about a 0.5% chance of this happening. You'll notice a dramatic change from before. When we had only 1 coffee at a time, we had an almost 15% chance that we would get something less than 400. But just with an average of 6, you're down to a 0.5% chance that that's going to happen. And later on, this is going to be more useful to us because we're going to say, well, are we really getting gypped on our coffee on a regular basis, or is it just random chance that we got a very underfilled coffee? If you only do 1 at a time, it's hard to make much of a statement of proof on that because 15%, that could happen any day. But a 0.5% chance, now you're really starting to talk about something that's very unlikely. So that's where this is going to help us out later. So let's do one more quick example. Number of people who ride the mega coaster each day averages 500 per day with a standard deviation of 900 per day. What's the probability that more than 5,400 people will ride the coaster on a randomly chosen day? Well, our standard deviation, 900, our our average, x bar here, is 5,000. So let's go ahead and label those right away. First question asks us, with our value of interest being 5,400, what is the probability that more than 5,400 people will ride the coaster on a randomly chosen day? Well, if you get to choose one random day, we don't have to worry about updating our standard deviation or anything, so we can go straight into finding a z-score. And our z-score is going to be our mean, 5,000. Oops. Don't let me catch you off guard there. We always do our x value minus our mean divided by standard deviation. So our x value is 5,400. And we subtract our mean of 5,000. And we divide that by our standard deviation of 900. So when we get our calculator, 5,400 minus 5,000 is 400, divided by our standard deviation of 900 is going to be 0.444. Since we want to know the probability of getting more than this value here, more than 0.444 is going to be about here on our normal curve and upwards. Since that's what we're looking for, we're going to do our normal CDF to go above that value. So normal CDF, and we're going to start on the left side at 0.44. And on the right side, we're going to go off to infinity. So we'll just pick a big number like 1,000. And when we do that, we get our normal CDF of, we'll just put that directly in there to avoid rounding error, comma 1,000. And we get 0.328. And so the probability that we could get more than 5,400 people on a randomly chosen day is almost 33%. So pretty reasonably likely to happen. Now, if we look at this slightly different problem here, it says what's the probability that the average of 35 randomly chosen days will be more than 5,400 people? Well, this time our value of interest is still 5,400, but our standard deviation gets updated by the fact that we now have a sample of 35 that are being averaged together. So we need to take our old standard deviation of 900 and divide it by the square root of our sample size. Divide that by the square root of 35. And let's see what that is. Divide that by the square root of 35. And we're looking at 152.1. So our standard deviation went down quite considerably. So now we do the exact same thing we did above. We're going to take our value of interest, our 5,400, subtract the mean, 5,000, and divide by our new updated standard deviation of 152.1. And this is going to give us our new updated z-score. So we're 5,400 minus 5,000 is just going to be 400 again. And we're going to divide that by the standard deviation here, which we have calculated above, so second answer. And we get 2.629. 2.629. Compared to our original z-score up here of 0.444, this seems pretty darn extreme. So we've really moved this up quite a bit. So if I were to sketch out that normal curve, instead of having this, which looks like almost half the normal curve, I guess a full third of the normal curve, we're going to have something that looks like this. So the probability of getting more than 5,400 people something real small up there. So again, we do our normal CDF, and we're going to start at this z-score here. We're going to start on the left side of the z-score we just found, 2.629, and then we're going to go off to positive infinity again. So we're going to go up until 1,000. So second vars to get our normal CDF. We're going to use our answer to avoid rounding error, and then we're going to type in 1,000 as our upper end. 0.004. We round it off to 3 decimals. So up here, if we just picked any random day, we had almost a 1 in 3 chance of being above 5,400. If you pick 35 random days and average them together, you all of a sudden have less than a 0.5% chance of getting more than 5,400 people. So again, the power of just having even a moderate sample size like this of 35 is incredible in what it enables you to do. Last thing to note with this particular problem is that at the beginning, I didn't check if I had a normal curve. In this problem, up on top where it says what is the probability of more than 5,400 people riding the roller coaster on a randomly chosen day, I assumed that we were dealing with a normal curve. It doesn't say anywhere in this problem that we were. And in fact, if you think about it, number of people riding coasters is probably somewhat bimodal. Maybe during the weekdays it's kind of low, and then during the weekends it's really high, or something like that. My guess is it's not a perfect normal curve. So this problem right here, although it sounds all nice, this value might not be realistic at all because I'm probably not dealing with a distribution that looks like this. The awesome part about the central limit theorem is that even though my starting distribution might be something crazy like this little sketch up here, this problem still can be solved. Because I have 35 randomly chosen days, the central limit theorem will turn that graph above into something that looks like a nice, skinny normal curve that I can use for my predictions. And therefore, even if this problem right here is completely invalid, even if this data is completely worthless, this down here is a valid calculation, and this result is something that I could actually use to prove a point. So again, central limit theorem is very powerful in all kinds of different situations.